Folks, I might be the greatest to ever do it. Welcome back to another video on duck game computing. I have a nice map here with all my register designs. You notice there's 4 of them now. So we got my original over here on the left. Then we got my item mount improved design here. Then here's the teleporter one I showed off like 2 videos ago. And here's my current one. Once again, we have brought the size of the circuit down by like 1/4. Yeah, let me show you how this thing works. I came up with this idea while I was messing with feed tapes, or the feed tapes gave me the idea. So you can see here we got our data line is this one right here. Every time I press the data line, you'll notice that TV shifts between the 2 trapdoors. Then we have our clock here, which just spawns a crate and also shoots the mag blaster. You can probably see where this is going. And then our reset just shoots whatever crate is on the output button. This is our output button right here. So just to demonstrate here, data line down. I hit the clock. The TV blocks the mag blaster, and the crate is able to spawn on the output button. If I remove the data line, the output stays on only until I clock it. Once again, the mag blaster this time unblocked is able to destroy the crate. And then of course, if I assert the data and I clock it and then hit the reset, the output gets turned off. So yeah, as a register, without any, I suppose in theory you could call the item shifter here with these 2 trapdoors, you could call that a latch, but I finally found a register design that doesn't rely on building it discretely out of logic gates, and I am very excited about that because this thing is way faster, way smaller, and way simpler than the other designs. So once again, Moore's Law exists in duck game. Every 2 videos I find a way to shrink my register design by or to decrease its size by 4 times. Anyway, today we're not just talking about registers. Today we're talking about shift registers. To demonstrate here, let me pull one up. Yeah, here we go. So just to demonstrate here, also I want to talk about, this is my previous design. For whatever reason, blocks didn't get copied over. This is my original concept for the item. We'll call it the item NAND gate, or the item register. It was just a single trapdoor dropping and causing the springs to shift whether it's on the left or the right. But it turns out it's way faster to do it like this. You can half-step the doors, but this makes the timing pretty unreliable on the input. You have to press this button down for a very specific amount of time to get it to work, and even then it's not consistent. So separate it out, slightly slower, much more reliable. Anyway, this is a shift register. So a shift register is just a bunch of registers in series. The output of this register feeds into the input of this register. Likewise, the output of this one feeds into the input of the next one. And effectively, if we clock all the registers at the same time, we're able to move a bit down the register. So I can show you what that looks like here. I have a bunch of items spawn cannons set. Let's slow this down just to make it a little easier to see what's happening. So I have a bunch of spawn cannons here set to clock every register at the same time. Right now it's set to clock once a second. There we go. And then I have an input flipper right here, so it just inputs a 0, then a 1, then a 0. You can see here. What you'll see is whether if a trapdoor is open, then the register's output is on. If the trapdoor is closed, the register's output is off. And as you can see here, the values slowly shift down the right to the right of the register with every single clock cycle. I can throw in a single here, and as you see, it just goes down by 1. Or I can just keep the output consistently on, and it continuously goes down until the full thing's full. Turn it off again, and it turns off again. I've built shift registers with my previous designs. The fastest I was able to get one to clock was at 1 Hertz, which is once a second. With this design, we can go up to at least 2 hertz, so twice a second. You can potentially go further, but you can't go below. You can't quite clock it 4 times a second, and with the item spawn cannon delay, you can only move by increments of quarter seconds. So potential to clock it faster, but just for demonstration here, we'll watch this thing go. Bam, 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 bam. It's crazy fast. So now if I input 1, turn it off and on, here I'm flipping it, and yeah, they're just moving down the register very quickly. So why is a shift register useful is a very reasonable thing to ask. So first off, very simply, a shift register is a very simple 2 times multiplier. So if you think about binary numbers, 1 is 1, 0, or 1, 0 is going to be 2, 1, 0, 0 is going to be 4. So if we keep shifting in a 0 on the right end of the number, we keep moving the 1 further up higher to a higher place in the binary number, and we're multiplying it by 2. So that's one useful application. There's a whole host of them. Here I have another one to demonstrate, which is that shift registers are very handy for converting parallel signals to serial signals and serial signals to parallel signals. What do I mean by that? Well, all right, so this is a demonstration I've set up here. We have on the left a feed tape reader that I demonstrated in my last video. Then we have a register. It feeds its inputs into a shift register. And that shift register here can get, I have a system here that will clock the shift register 8 times and use that to spit out a new feed tape of the values stored in the shift register. So effectively what this is doing is it's taking the serial input of the feed tape. The feed tape reader reads the feed tape serially, so it does it one by one. Not all items at the same time, but just takes off the bottom one, reads it, sends off that info, then reads the next one. It takes that serial data and puts it into the shift register. And from there, since every single bit of the feed tape is stored in its own register, we could do something with all those values at the same time. So I could I could read out all of these values just by checking the output of each register. I could feed all of those values into like an 8-bit adder or something. So I could process those values in parallel. And then likewise, if I have a parallel signal, I can feed it into a shift register and then clock the shift register 8 times, read it out one by one to convert the parallel signal back into a serial one. So let me demonstrate that here. So we're going to read in a feed tape here, and you'll notice it copies it into the shift register. A closed gate is a TV, a closed trapdoor is a TV, an open trapdoor means it's a present. So what we have here, reading from right to left, is a TV, present, 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 TV, TV, present. So if we look at the bottom, TV, present, 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 TV, TV, present. So it's read it in properly into the shift register, and now if we want to read it out, I hit this button, it will clock our shift register 8 times, and then read the rightmost shift register each time. This is not the most efficient way to create a copy of a feed tape. I mean, that you can clearly see with the previous video. More so just a proof of concept here, converting serial data into parallel data back into serial data. So yeah, that's one incredibly useful value of shift registers. Now, let me show you an actual practical application of this. Because that's plenty of theory. Let's see some real world examples. If you've ever been to, say, a hotel before, oftentimes they have, for your valuables, they'll have a programmable safe. You can, if it's completely reset, you can enter a combo, it'll save that combo, and then the next time you enter that combo correctly, it'll unlock the safe for you. And then once you have entered that combo correctly, you can choose to reprogram the safe. And using if you were to design that in a real world setting, you would do it with shift registers. So let me go ahead and show you. That's exactly what I've done. Shift registers, combo lock. Here we go. Here's the madness. So let me turn off my webcam here so I don't cover the entire thing. There we go. So what we have here is 2 shift registers. We have one at the top 8 bits long. We have one at the bottom 8 bits long. The top register saves whatever input we're entering at the given time. The bottom register saves the combo that we're trying to control. So let me go ahead and demonstrate. Here I can. So because my shift register only can store 1 bit, I only have 2 inputs, 0 and 1 for the combo lock entry. So here I've entered a 1. Here I've entered 2 1s. Let's do a 0. So if you look at the top shift register, you can see by the you can tell by the XOR gates beneath the shift register how the values are moving along. So here's another 1. So you can see the item crates are rapidly moving through some of the teleporters. In other cases, the item crates are stopped on the button. So you can see how the values move down here, and let's just fill in a bunch of zeros here. So right now, the combo at the top does not match the combo at the bottom. So when I hit this button, which would unlock the safe, nothing happens. So now let me go ahead and reset the entire system. Here, clears everything out. All right, so right now, both shift registers have the value just all zeros across the board in them, which means that the door will unlock because they match, which is what we want. We just reset the safe. So if I go ahead and hold down the unlock, I go ahead and reset it, and now everything's 0. I go ahead and hold down the unlock. Now what I can do is I can hit the reprogram button. So I hit this button, and now the next 8, my next 8 inputs will get saved as the new combo. You can see over at the top right, there is a stack of boxes of wooden crates. That's my counter. That's my my 8 my counter that goes up to 8. And you can see every time I enter here a 1, it goes down 1. Now let me do a 0, 1, 0, 1, 0, 1, 0. Now, there we go. It clocks the bottom row. Now that's saved. You can see by the trapdoors on the bottom shift register, you can see the value stored is 1, 0. Reading from right to left is 1, 0, 1, 0, 1, 0, 1, 0. And then automatically in the process, the top row, after it saved that combo, got reset. So the top row is completely cleared. So now if I hit the unlock button, nothing happens. Only when I enter the saved combo will the safe unlock. So let me do that again. 1, 0, 1, 0, 1, 0, 1, 0. I think we got 2 more digits to enter. 1 and 0. To do it. There we go. So now the same combo is entered. And I can go ahead and press the unlock button, and there we go. And just to further prove it, if I take away the unlock button and then I add 1 more value in here, now the values don't line up anymore, so I try and unlock, it doesn't work. Don't get me wrong, there are much simpler ways to build sequential combination locks in Duck Game, using Duck Gamey properties and items, that sort of thing. This is how you would build this is how you would design this kind of lock in like real world digital circuitry. You would likely use 2 shift registers arranged like this with the same kind of connective logic. So just to have a closer look at some components of this, so it's not just a jumbled mess. I already pointed out the top shift register up here and the bottom shift register down here. Internally here we have a bunch of logic on the outputs. So every single register pair, so this one and this one, every single register pair. So this one and this one feeds into an XOR gate. So this XOR gate right here. Teleporters have a bit of a property where they'll clip slightly into or boxes being shot next to teleporter will in fact clip into them if they're moving right adjacent to them. So this crate gets shot out here into this teleporter, which goes to this teleporter, hits this button, activates activates the XOR gate. The same thing happens down here. So each register pair feeds into one XOR gate. You can see this happen down the line up until the last register pair here feeds into this XOR gate. And each XOR gate's output feeds into an AND gate. Something very useful I learned, actually, let me go ahead and just show this right now. For creating multi-input AND gates, you can see I'm not using any half steps here. If you look at trapdoor sliders, you can move it from 1 to 4, and then it can go to 6 outside of the range, and it looks like it only appears to work as 2. I should have tested this way sooner, because it turns out, yeah, they actually work out to 6 blocks. So you can see up here, the 6th block is where I fall off. incredibly useful to have even longer trapdoors. For this purpose, we have, a couple of 4 input or less trapdoors here. On the outside, we have 2 6 inputs. So we're feeding 5 of our XOR gate inputs into one AND gate, and then that's feeding into another 5 input AND gate, which adds the first 5 input as well as the final 3 XOR gates, and then also our unlock signal here feeds down into here through this teleporter into this input. And if all of those, all the inputs, the AND gates are on, then the output to the entire network is on, which first of all unlocks the door through this teleporter here, and then also enables this AND gate here, which is connected up to the reprogram button through this teleporter, which goes all the way over here. Hits this button to open up this AND gate. When that AND gate gets activated, because I press the reprogram button, this latch is flipped, and it will remain so until I enter 8 digits. Every single clock signal gets fed through these teleporters up here. Till I enter 8 digits, and then it will count down 8 here. You can see this mag blaster is here angled at this block, so it only actually destroys one crate. If you shoot your crate directly, it'll also destroy the one above and below it. So this is a nice way to destroy one crate at a time. Every single clock signal breaks one crate. Up until all the crates are destroyed, this button turns off, which first of all spawns a new line of crates, and then also spawns a cannon down here that clocks this row of registers through this teleporter here. This crate here goes down into this teleporter, clocks all these registers, and then also switches this latch back to off, so that I can't reprogram the safe again until I enter the correct combo again. And the final security measure is to clear the combo out of the top row, which is done here. This over here clocks all the reset lines, all the resets of the top row. The final piece of the puzzle is how the outputs of the top row shift register gets to the bottom shift register, and that happens through a very fun series of just trampolines and teleports. I gotta say, I love teleporters. Wires are an awful way to transmit data. I've been over that before. Teleporters, you just plop 2 down. Doesn't really matter what's between them as long as there's no other teleporters. And you send an item through it. It makes no noise. It's virtually lagless. God, 10 out of 10 item. Thank you, Landon. But yeah, so you can see here when I input any kind of combo, the blocks are raining down from the top row of registers into the bottom register. And we got to move them over to the side slightly, just because, you know, the output is a lot further to the left than the input of each register. So the inputs come down there, and then whenever we need to clock it, all the inputs get copied. And yeah, that's pretty much all there is to it. If you'd like a funny throwback and another explanation of how this sort of thing works, I actually made a video like 3-4 years ago building this exact same thing in Minecraft. I'll link that in the description as well. Although I should say in that case, I'm using 16-bit shift registers rather than 1-bit shift registers. We are Minecraft is a very powerful game for this sort of thing. Duck Game is not. But yeah, that's about it. All I got for today. The next upcoming videos will probably be more having to do with feed tapes, because that's what I've been fiddling with, but I haven't made that yet, so we'll see. Yeah, that's about everything. I'm the GOAT. Thanks for watching. I'll see you guys later. Bye-bye.